Well, my dear students, now we are going to start the 26th lecture in the series of mechanics of metal forming. As you are aware of, the last lecture we continued with limit analysis. We discussed what is actually limit analysis, and the two versions, that is the lower bound and upper bound, that we are going to deal with under limit analysis. So we discuss the lower bound theorem, and we took few examples as well, as based on the theorem we took few examples. So we would continue the last lecture today, and this application we would continue with more examples, and at the end we would introduce the upper bound theorem. So if you recall back, so last time that the lower bound we considered the application for indentation of semi-infinite body under pressure P. So look at the figure again here, where the pressure P is applied, and the two zones, that is the segment 1 and segment 2, has been identified here in this figure A and B. So you know the stress sigma 2, that is in the zone 1, is 0, whereas in the zone 2 it becomes equal to P, and because indentation is in the one part of the whole body, so and accordingly the pressure P is there. So to draw the Morse circle diagram under this situation, so and the continuity condition for the traction, if you see the sigma 2 in the figure has a jump from the value 0 that is told in segment 1. So this jump is from 0 to minus P in segment 2. So the state of stress in segment 1 is represented by the origin, therefore in the figure if you look, O, origin O, in sigma tau plane, that is the stress and shear stress, normal stress and shear stress plane, and that has been shown in figure number 5. So this point also represents the plane in segment 2 on which sigma x is equal to tau xy, and both are equal to 0. So therefore an orthogonal plane on which sigma y is equal to minus P and tau xy is equal to 0 is represented by a point that is minus P and 0, and thus the radius of the Morse circle would be P by 2 simply, and for the material of segment 2 to yield according to the Tresca criteria, as I said, one has to choose a yield criteria. So the radius of the Morse circle must make K, that should be the radius, and therefore here P becomes equal to 2K, and that is what has been marked here in equation 33, and P is equal to 2K is a lower bound estimate for the traction, therefore. So an improvement in the lower bound estimate occurs if the segment 1 is also assumed to be on the verge of yielding. In this case, the stress component in this segment can be assumed to have the value which is sigma x is equal to minus twice k, and sigma y and tau xy is equal to 0. This stress state is represented by a Morse circle of radius k and center minus k 0. You can look here at the figure. So, the stresses, that is sigma x is equal to minus twice k and tau xy is equal to 0. So, this remains the same in segment 2 as well on account of the continuity, and the Morse circle for this segment must therefore have a radius k if the material yields following the Tresca yield criteria. This is possible if sigma y is allowed a jump to how much? Minus 4k. So, this traction boundary condition, that is sigma y is equal to minus p, is satisfied by the choice, and therefore p becomes equal to 4k, and that what has been shown here in equation 34, which is an improvement on the earlier lower bound estimate for traction, which was 2k. For further improvement in the estimate of the traction, one can divide the body in 3 segments, like segment 1, segment 2 and segment 3, and this has been shown in figure 96. So, if you look here in the figure, segment 1 and segment 2 have common boundary, that is A1B1, A1B and A1B2 is the boundary between segment 2 and segment 3. Suppose the lines A1B and A1B2 are inclined at an angle phi on each side of the vertical line through A1. Suppose the material in segment 1 is on the verge of yielding. So, the stress in the segment can be assumed to have components like sigma x is equal to minus twice k, sigma y is equal to tau xy, and that is equal to 0. So, this stress state is represented by a Morse circle on radius k and center at C1, that you can see in figure 6 here. So, if you look at these regions, the region 1 that bisects the line A1B, the region 2 that bisects by the vertical line A1B1, and the region 3 that is bisected A1B2, and corresponding the circles are drawn. So, this is what is the difference with 2 region with the 3 region case. So, if you look at center at C1, which is in sigma and shear stress plane, that is the normal stress and shear stress plane, and its origin O represents the stress sigma y, which is equal to tau xy, and that is also equal to 0. So, on horizontal planes, a line drawn from O, which is parallel to AA1, cuts the Morse circle in region 1 at pole P1, therefore, one can see here in the figure. In this particular case, the pole also represents stress, that is sigma x is equal to minus twice k and tau xy is equal to 0. So, one can draw a line through P1 which is parallel to A1B, which cuts the Mohr circle at Y1. Okay. The line, therefore, the line P1Y1 makes an angle that is pi by 2 minus phi with P1O, and therefore angle Y1C1O, which is equal to twice of the angle Y1P1O, and that is equal and to and nothing but pi minus 2 phi, one can see here. So, the normal and shear stress on the plane, which is represented by Y1, are sigma 1, which is equal to minus k cos 2 phi, and tau is equal to k sin 2 phi respectively. Therefore, so this plane is the common boundary between segment 1 and segment 2. Therefore, the point Y1 is common to Mohr circle for the two segments. In other words, it lies on Mohr circle for segment 2 as well as, that is all. So, you mark these regions here. The O is on the right hand side, the C1, C2 and C3, and the Y1 and Y2 points are located here. Alright. So, the angle between planes A1B and A1B2 equals how much? 2 phi. Hence, the chart Y1, Y2 of the Mohr circle, which is shown for region 2, makes an angle 4 phi at its center C2. One can see the line Y1C2 is tangent to the Mohr circle of segment 1. A line through Y2 which is perpendicular to the radius C2Y2, it cuts the stress axis at C3, one can see. The center of the circle, that is the Mohr circle for segment 3. That means all the three segments are assumed to be on the verge of yielding. Therefore, all three Mohr circle which has been shown here have radius equal to k. The distance of the point C, which represents the plane A1, A2 from the origin of stress, normal stress and shear stress plane, is therefore what? That means it is P, and that is equal to minus k sin 2 phi minus 2 k cos 2 phi minus k sin 2 phi, and if you simplify this, this becomes equal to 2k multiplied by 1 plus sin 2 phi plus cos 2 phi. So, the value of phi which maximizes P is what? It is a pi by 4, and the maximum value comes out to be, that is P max comes out to be 2k multiplied by 1 plus root 2, and that is what is equal to if you calculate 4.83 k, and this is what's the lower bound estimate. Now you see that the lower bound has now further improved. In the first case it was 2k when there was two regions. When we considered the three regions, the value improved to 4k, and when we further did it this manner, it is further improved on the maximization to, that is 4.83 k. and that is the base lower bound estimate for the problem of indentation. Is this okay? So, this is how one can proceed for the lower bound solution. Now, let us take another example. Another example where the sheet drying is done through a taper die. So, look at this figure. If you look at this figure number 7 here, 7a particularly, where a sheet is drawn through a die of semi-angle alpha. The drying operation, because it reduces the sheet thickness from height 2h to 2h is small 2h, and therefore the reduction is small r, which can be calculated as 1 minus small h by capital H, and this has been shown in equation 35. So, for a lower bound analysis, one can consider the upper half of the sheet, which has been shown here in figure 7a. So, if you look at the upper half, so this region, again there are 3 regions has been identified, that is region 1, region 2 and region 3, and a small element has been shown, and where the different stresses are acting on this small element in all the 3 regions. So, look at the line AC and CB and BA. Okay. So, the upper half of the sheet, and let us divide it into 3 segments as I said, and this has been shown here in part B. So, if assuming that there is no force is applied to push the sheet through the die, that means the back tension is 0 simply. That means consequently the vertical planes in region 1 remains stress free. The horizontal planes are subjected to stress, that is sigma, which is equal to minus p, and shear stress is 0, where p is twice k, assuming the material in region 1 to have reached the yield point, otherwise p is less than 2k. Okay. So, the stress state is represented by the Morse circle in the region 1 of the radius having p by 2 and center as C1. One can see the origin O of the stress plane that represents the stresses 0 0 on horizontal planes, and the coordinates as minus p and 0 of p dash, that represents the stress on vertical plane in region 1. One can see here. The point O is also the pole P1, and let a line which is drawn through the pole is parallel to the plane AB, dividing the zone 1 and zone 2, and cut the Morse circle in region 1 at A1. It represents the stresses, that is half P 1 minus twice cos theta and half P sin 2 theta on the plane common to region 1 and region 2. The point therefore lies also on the Morse circle for segment 2. The radius of this circle must be k, since the material in region 2 must yield for a successful drying operation. Its center C2 is located on stress, that is the sigma axis, at a distance k from A1, one can see. So, the Mohr circle in region 2 for the second segment is drawn with radius k from the center C2. Let an extension of the line, that is A1 P1, intersects the circle at P2, which is a pole, and suppose a line through P2 which is parallel to BC intersects the stress axis at A2. So, the distance OA2 is the normal stress on the die AC, and suppose a line through P2 which is parallel to the common plane BC in region 2 and region 3 intersects the circle at point M, which must also lie on the Mohr circle for the segment 3, and it intersects the sigma axis at point T. So, the center C3 of the Mohr circle for the segment 3 is located on the sigma axis and the perpendicular bisector of MT. Alright. So, the Mohr circle region 3 of radius C3 T and center C3 completes the diagram. You can look at this diagram, part B, figure 7. You can note down the distance OT that yields the lower bound estimate for the traction T, which is required for drying. So, if you look at this, so the T becomes what? T becomes OT, and OT is summation of ON2 plus N2T, and that is nothing but N2 P2 multiplied by cot theta plus cot phi, and this has been shown here in equation 36. But you know N2 and P2 is equal to 2k sin alpha cos alpha, and that is also equal to k sin 2 alpha, and capital H minus small h from the drawing can be calculated as AC sin alpha, and that is equal to h cot theta plus small h cot phi multiplied by sin phi divided to the whole as cos alpha, and this is shown in 37. So, using these, the reduction formula, if you use these equations and the reduction formula, so the reduction formula would yield, that means it is cot theta plus cot phi will be equal to R. R is the reduction multiplied by cot alpha plus cot phi, and therefore the traction T required for the drying can be expressed in the form of the equation which is shown here in 39. That means T is simply R k sin 2 alpha multiplied by cot alpha plus cot phi. So, the reach for the maximum value for T depends on finding the maximum permissible value for cot phi, if you look at the equation 39. So, for this purpose one can assume that the material of the segment 3 is at the yield point, and in this case the radius of Mohr circle in the region 3 is therefore k, and therefore angle C2 C3 capital M is equal to angle C3 C2 capital M, because angle M P2 A2 is simply pi by 2 minus alpha minus phi, and that is also equal to angle C3 C2 M by 2, and angle M P3 A2 is equal to phi, and that is also equal to angle C2 C3m by 2, and therefore one can say that phi is nothing but it is equal to pi by 4 minus alpha by 2, and therefore T is 2k multiplied by 1 plus sin alpha multiplied by r, and this what has been shown here in equation 40. So, this is the lower bound estimate for traction T, alright. So, a comparison can be made, and if you a compression, suppose it is taken with P which is applied to the push, which is applied to push the seat through the die, results in a shift of the diagram by the same amount to the left along the stress axis, and the tension required in this case is therefore T, which is 2k 1 plus sin alpha multiplied by r minus P, that is the push. So, this has been shown in equation 41. So, the lower bound theorem can also be used for bodies with curved boundaries. The expansion of a thick tube is taken as an example for this problem. So, we can take up this another example where expansion of a thick tube is taken and where the body is curved now. So, let us start with this case, and let us consider the expansion of a thick cylinder tube which is and having a pressure, internal pressure as small p, which is applied at the inside radius a, alright. So, the outside radius b is assumed free of any traction. So, assuming the deformation to be axis symmetric, the equation of equilibrium for such problem can be expressed in polar coordinate, because it is a symmetrical body, tubular body. So, if we express in the polar coordinate in the form, so that can be represented as deva sigma r divided by deva r plus sigma r minus sigma theta by r, and that would be equal to 0, where sigma r and sigma theta are the radial and hoop stresses. In order to show the application of the lower bound theorem for this particular thick tube expansion example, the form of radial stress is assumed to be, that is the sigma r is equal to capital A r plus b, if it is assumed. So, the boundary condition prescribed at the inside and the outside radius would be, that can be given as capital A is equal to minus capital B by small b, and that is simply equal to P by small b minus small a. The partial derivative of the radial stress therefore yields that deva sigma r by deva r is equal to a, and that is nothing but equal to P by small b by minus a, and the equilibrium equation, the equilibrium condition will yield, that is the sigma theta minus sigma r, and that is equal to P r divided by b minus a. If the material obeys traction yield criteria, let us, so then one can say that the mod of the sigma r minus sigma theta should be equal to how much? it should be equal to simply 2k, and that what has been shown in equation 46 here. As you know, the k is the yield stress in a shear. The above two relations, that is 45 and 46, yield an estimate for P. In making an estimate, a choice has to be made for radius r such that the yield stress is reached somewhere and the yield criteria is not violated anywhere in the cylinder. That has to be taken care. So, these requirements limit the choice to r is equal to b, and therefore, P becomes equal to twice k 1 minus a by b, and that what has been shown here in equation 47, and therefore, the P is equal to 2k 1 minus a by b is a lower bound to the exact solution for the pressure, which is P is equal to 2k log b by a. Alright. So, please note that a choice of r is equal to a is taken such that sigma theta minus sigma r is equal to P a divided by b minus a, and that is what is equal to 2k. This violates the yield criteria for all r value, all reduction value r. Alright. So, this is what is the example, and the lower bound is calculated. Alright. So, now up to these examples gives you how to work out for the lower bound solution and how one can improve this solution to some extent. So, you see, we started with the stress field. We have to go for the stress field, draw the Mohr circuit diagram, and then apply the yield criteria, and then find out the values of the field variables. But please remember that the lower bound solutions are mostly used for structural engineering application. For us, upper bound is more important. So, let us see upper bound theorem, because the upper bound theorem where an upper bound solution is required to satisfy only the kinematic conditions in terms of strain increments or the associated strain rates in a plastically deforming medium, and does not necessarily satisfy the stress equilibrium equation as we have seen in lower bound solution. So, an important concept that involved is that of a kinematically admissible velocity field. This is most important for upper bound. So, the velocity field that satisfy the constant of volume constancy and the velocity boundary conditions are called kinematically admissible velocity or deformation field. So, the volume constancy has to be satisfied and velocity boundary condition has to be satisfied. So, any velocity field that satisfy these two, we would call it as a kinematically admissible velocity field. That means, a kinematically admissible velocity or deformation field may have discontinuities in the tangential component along certain surfaces, but the normal component must be the same on both sides of the such surface in order to satisfy the constraint of incompressibility. So, the unknown parameter in the kinematically admissible velocity field are determined using the upper bound theorem. Alright. The value of the load estimated is not a unique one, but will depend upon the pattern of deformation proposed, and the least value of the upper bound is the base value. So, one can propose many such velocity field, but the one that proposes the least value of the upper bound is the base value. So, if upper bound method is used correctly, a very realistic overestimate are obtained, not underestimate. Lower bound may be a underestimate, but here we always go for the upper estimate or the overestimate, which will be minimum. So, to start with, let us consider a plastically deforming body, which is shown here in figure 8, that has a volume V, and the surface area is say capital S, which is subjected to surface traction Fi. Alright. Alright. So, now this is what is the body where the deforming body may have, now you look at, there is a discontinuities in the tangential component along certain surfaces, one can see, and this surface, say it is SD, which is shown here, SD, that is the surface, but the normal component must be the same on either side of the discontinuities to avoid any pile up of the material or cavity formation. That is, the tangential components can be UD and UD plus DUD, but VD must be equal to VD prime, that has been shown there. If sigma ij is the stress field associated with this particular surface traction Fi, so the displacement, that is dui, and the strain increment, that is d epsilon ij, then the principle, if we apply the principle of virtual work which we discussed last time, one can calculate that the over the integral over this particular surface Fi dui ts will be equal to the summation of two integral, number one as the over the volume integral, that is sigma ij d epsilon ij dv, and the second integral, which is the summation over the integral over this discontinuity surface SD, and that is the shear stress multiplied by the mod of the displacement discontinuity, that is dud, and that is for the small dsd surface. Alright, and this has been shown here in equation 49. So, the second term, if you look at the figure 49 on the right hand side of the above this particular equation, it has been added to account for the additional work associated with the discontinuities. So, here tau, which is the shear stress component of sigma ij, it is in direction of the discontinuities. So, if the actual displacement increment field that is du, and say other assumed incremental displacement field which is kinematically admissible is taken as du star as we had been doing earlier. So, such that dui star is equal to dui on the surface SU, that is dui is prescribed over the part of the surface SU, alright. So, further both the fields satisfy the incompressibility condition, that is deva ui star divided by deva xi is equal to 0 and deva ui divided by deva xi is also equal to 0. So, let d epsilon ij star be the strain increment which is derivable from dui star. Therefore, equation 49 can be simply written as which has been shown here in equation 50, alright. So, it becomes the integral over the surface S on the left side of like fi dui star ds, that is the kinematically admissible field, and that is equal to the two summation as number 1 over the volume, that is sigma ij star multiplied by d epsilon ij star dv plus summation over the discontinuities, that is over sd tau and mod of du d star d sd star over this particular discontinuity surface, where you know that the du d star is the discontinuity in tangential component on a discontinuity surface which is sd star for any kinematically admissible displacement increment field. So, the left hand side of the above equation in 50 can be very well written as, that is the integral s fi dui star ds becomes equal to the integral over su fi dui dsu plus over the surface f, the second surface f fi dui star dsf. So, this has been shown here in 51, alright. So, we will continue further from equation 51 onward, and we will proceed in the next lecture the rest of the part of this upper bound theorem. So, I thank you very much for your patience, keeping patience, and when we next time meet, please revise these equations so that we can start directly next time. Thank you.